Welcome back to the course entitled Symmetry, Stereochemistry and Applications. In the last week, we were discussing about substitution and elimination reactions, and we have discussed a few examples on substitution and elimination reactions in the last class. So, today we are going to start in this new week discussion on the addition reactions to carbon carbon double bond and CC triple bonds. So in this week, we will discuss about these following reactions. We'll talk about the addition reactions to alkenes, Markovnikov's rule, stereochemistry of ionic additions to alkene, sulfuric acid addition to alkene, water addition, oxymercuration and demercuration, hydroboration oxidation, addition of bromine and chlorine to alkenes, stereochemistry of dihalide additions, halohydrin formation. Then we'll talk about the divalent carbon compounds, that those are called carbenes, and then additions to alkenes, additions to alkynes, oxidative cleavage of alkynes, and then we will discuss about various oxidation and reduction procedures that are generally done in the organic chemistry laboratories. So, to start with, when we think of addition reactions, that means we are talking about saturation of a unsaturated carbon compound. So, for example, if we have a CC double bond, as is shown here, and if we want to add a substrate which is AB, maybe unsymmetrical or symmetrical, then this A and B gets added and the double bond is converted to a single bond. So it is very similar to the addition of hydrogen. You may have learnt in your 10 plus 2 how the hydrogen is added to a CC double bond. So we will now discuss the reaction mechanisms of addition of unsymmetrical substrates to a CC double bond. So we will discuss the addition of various HX, halogens, sulfuric acid and water in a systematic manner. So why do these addition reactions work? How does this reaction proceed? So in this addition reaction, you see that we convert one pi bond to two sigma bonds. You had a CC double bond, and from that we have converted it into a CC single bond. So what has happened is we removed one pi bond and created two sigma bonds, and normally this process is energetically favored. The two sigma bonds are higher energy than one pi and one sigma bond. So as a result, in general, the overall process is typically exothermic. What do we mean? If we draw the energy profile, if we draw the energy profile diagram of this reaction, if we have this alkene at this level, it goes through a transition state and the product is generally more stable. The addition product has more stability than alkene, and therefore it releases this amount of heat, which is a phenomena of exothermic process. So pi electrons are exposed above and below the sp2 hybridized carbon atoms, and these pi bonds are good for capturing electrophiles like H plus ions, Lewis acid and halogens. Even the metal ions with vacant d orbitals are also good electrophiles which can form bond with these pi electrons. So let us look at the addition reactions of some hydrogen halides. So when you try to add a hydrogen halide to alkene, what happens is the first step is the step of breaking of this pi bond. So the pi bond is broken and the electron is donated to the H plus and it forms this carbocation and Br minus is released. And then in the solution when we have Br minus, this Br minus gets attached to the carbocation site and forms the addition product. So this particular reaction has a general trend of reactivity with Hi being most reactive and Hf being the least reactive. This reactivity order depends on the bond strength of Hx. Higher the strength of this bond, lower is the possibility of reactivity because in this first step, the bond breaking of Hx takes place. So this sigma bond is first broken and the proton is added to one of the carbon atoms and bromine is released as Br minus. Usually we do this reaction dissolved in some solvents. Sometimes it is possible that the Hx is bubbled through a solution of alkene in a solution. So when we try to understand the addition of HBr, what we see is that the pi bond, which is the nucleophile, it first gets protonated and forms the carbocation as intermediate, as you can see here. This is the carbocation intermediate. Then this carbocation takes up the Br minus, which is the nucleophile. So HBr gets added and this addition happens in overall two steps. H plus and carbocation are respective electrophiles and this is a symmetric alkene where this addition reaction we have discussed. So in case of symmetric alkene, it does not matter whether on the first carbon or on the second carbon the H plus gets added. But this becomes important when the alkene is asymmetric. That means the two carbon atoms C1 and C2 have different substitutions. Let us see what happens in those cases where the alkene is non-symmetric or asymmetric. So in this case what you can see is here carbon 1 and carbon 2 are different. Carbon 1 has 2 hydrogens and carbon 2 has 1 hydrogen. If you do HBr addition to this alkene using dichloromethan as solvent at 0 degree centigrade, we get two products with very much different percentages. Bromine added to carbon 2 is the major product and bromine added to carbon 1 is a minor or a trace product. So 2-bromopropane is observed as the major product in this reaction. And this is true with other alkenes as well. So here if you have two carbon atoms connected to carbon number 2 and two hydrogens attached to the carbon number 1, addition to the carbon number 2 with bromine is the major product and addition of bromine to the carbon number 1 is minor or trace product. How does this happen? What is the reaction mechanism in this case? So this reaction goes through the formation of carbocation, which we have already discussed. So the product distribution is explained by looking at the reaction intermediates. So if you have this compound, you try to add H plus. So if H plus is added to carbon number 1, you get this carbocation. If H plus is added to carbon number 2, you get a different carbocation. Now, if you compare the stability of these two carbocations 1 and 2, what you see is that this carbocation 1 is a 2 degree carbocation, while this carbocation 1 is 1 degree carbocation. And we have already learned in our previous week's lecture that 2 degree carbocations are more stable compared to 1 degree carbocation. Therefore, this 2 degree carbocation is more stable, and hence this forms much more amount. As a result, when the bromine is added, Br minus is added, it is added to carbon number 2 and not on carbon number 1, and therefore you always receive this compound as major product and the other one as minor or trace product. So what we have learned is that the 2 degree carbocations are more stable than 1 degree. So the major product formed from the most stable carbocation as the intermediate, and hence the transition state for 2 degree carbocation pathway is lower in energy, and hence it has a lower energy of activation. And then that is why this reaction is favored to form the major product as 2-bromopropane. So what we are trying to make out here is that when you draw the reaction coordinate with energy in y-axis or reaction coordinate in x-axis, suppose this is your alkene. If it goes through the 2 degree carbocation pathway, it forms the product here. If this goes through the 1 degree carbocation pathway, it is the product here. So the E act for the carbocation pathway 1 is more compared to the E act for the pathway with carbocation of 2 degree. Therefore, the product which forms through the carbocation formation of 2 degree carbocation is more stable, and it forms in more quantity. Therefore, you get a large difference in the amount of 2 different addition products. And this particular observation that this path goes through a carbocation pathway leads to a rule called the Markovnikov's rule. So what does this rule state? It states that in the ionic additions of an unsymmetrical reagent to a double bond, the positive portion of the adding reagent attaches itself to a carbon atom of the double bond so as to yield the more stable carbocation as an intermediate. So this statement clearly is dependent on the stability of carbocation. So for example, if we are trying to add ICl, we clearly know that I is delta positive and Cl is delta negative in this particular compound. So the positive part of this adding reagent attaches to the double bond in such a way to generate a more stable carbocation, which is a 2 degree carbocation, and then this 2 degree carbocation takes up the Cl minus and it forms this compound as the major product. This preferential addition of unsymmetrical reagent to this alkene is called regioselectivity, which we will discuss in detail in the next week's lectures. So when we try to see what happens when we have a compound which is a prochiral molecule, when we try to add HBr to such a prochiral molecule, the first addition of hydrogen generates 2-degree carbocation, and this 2-degree carbocation is a planar molecule, and as a result this planar molecule can take up from the bromine from the top and bromine from the bottom. So if bromine comes from top, the two bonds which are on the plane is pointing downwards, and if the bromine adds from the bottom, then the bonds which are on the plane points upwards. So this top attack or top capture of bromine and bottom capture of bromine results into two different compounds which are essentially a pair of enantiomers. So in this reaction, using a prochiral compound, we could generate a pair of chiral molecules which are pair of enantiomers, and needless to say that these two faces of the carbocation are equally populated, equally accessible to the bromine atom or bromide ion, and hence it gives rise to a racemic mixture of these two compounds which are enantiomers. So we end up getting a racemic mixture of a chiral compound. Now let us see what happens when we try to add sulfuric acid to alkenes. We must add cold dilute sulfuric acid to form this alkyl hydrogen sulfate. So when you add this sulfuric acid, the double bond takes the proton and bisulfate anion is released, which in turn then gets bonded to the carbocation and forms this bisulfate addition product. So this is, again, the mechanism is similar to the mechanism of HX addition, and it also obeys the Markovnikov's addition rule. But then what happens is this bisulfate gets hydrolyzed in presence of water when the solution is heated mildly, and HSO4 minus is released and water gets added. So again, the net reaction is the addition of water to alkene and it forms an alcohol. So this reaction is generally used in industrial process of ethanol making. So when you try to add water to alkene, which is called the hydration reaction, it is generally acid catalyzed addition of water across a double bond, and net reaction is Markovnikov addition of water to this alkene, and you can see that one proton gets added to one of the carbon atoms, the OH group gets added to the other carbon atom, and it is in the presence of H plus, which is maybe dilute sulfuric acid. And in this particular type of reactions, it is possible to have a rearrangement of carbocation if possible, because if there is a possibility of hydride shift or a methyl shift, then the hydride or methyl shift may happen and you may end up getting a more stable carbocation from a 2-degree carbocation. For example, in this case, if this hydride is shifted from here to this site, then we would get a carbocation formation at this point where it is a 3-degree carbocation, and you may end up seeing a product where the OH is not connected to this carbon, rather OH gets connected to the 3-degree carbon site and forms a new product. So when you encounter such a situation, you need to look at whether there is possibility of any hydride or methyl shift, which may result into a more stable carbocation, and hence you will see a different product that is being formed. Now let us see a different reaction called the oxymercuration and demercuration reactions on alkene. So when you treat an alkene compound, a double bonded molecule, in the presence of water and mercuric acetate in THF solvent, THF is tetrahydrofuran, which is used as a very common solvent. The first step of this reaction follows Markovnikov addition rule, and the OH and HGOAC are added across the double bond. And in case of demercuration reaction, in sodium hydroxide and NaBH for sodium borohydride, which is a reducing agent and also a supplier of hydride ion, you can get the HOH addition, that is addition of water to alkene, and both the reactions are quite rapid, and this yield is nearly 90%. Sodium borohydride acts as a hydride delivering agent, and this also happens through the Markovnikov process. So if you have the unsymmetrical alkene, this goes through the Markovnikov addition process and forms a product which is a Markovnikov addition product of water. This type of reaction can be done on cyclic alkenes as well. So in case of cyclic alkene, you get the intermediate like this, as we see here, and then on reacting with sodium hydroxide, sodium borohydride, you get the water addition product. But what we see here, very important, is that rearrangement of carbocation is not observed in most of the cases. So why does it happen? Let us see in the next slide. This oxymercuration demercuration process goes through the formation of a carbocation where the mercury is bonded to two carbon atoms simultaneously because of its very large size, and this 2-degree carbocation is not possible to go for any rearrangement to go for a 3-degree carbocation, because this mercury forms a partial single bond with both the carbon atoms, and it does not allow for the formation of or shift of hydride and form a more stable carbocation. Therefore, in this particular mechanism, you do not get a variety of product, rather you get only one product. If we do the same reaction with a slightly different reagent, we try to add water, but we add this water using hydroboration oxidation mechanism. So if you treat this alkene with BH3THF medium, first it forms this boron compound, trialkyl borate, and then that trialkyl borane is hydrolyzed by H2O2 NaOH or oxidized to form this compound, which you see that is an anti-Markovnikov product. So in this process, water is added across this double bond in this way. H gets added here and OH gets added here, compared to all the previous cases where H and OH were getting added in the opposite direction. So here what we see is called the anti-Markovnikov regioselectivity or regiochemistry, and this reaction also proceeds through syn stereochemistry. So if you had a double bond as shown here, the first step is borohydride addition, BH3 addition in THF, and then oxidation by H2O2, what we see here is that H and OH are delivered from the same side of the double bond. So if it is either delivered both from bottom or both are delivered from top, and hence this mechanism is called a syn addition, and this addition follows anti-Markovnikov product or anti-Markovnikov mechanism. So when you try to add chlorine or bromine to alkene, it's very easy. You can bubble chlorine or bromine through a solution, or a solution of bromine or chlorine in CCl4 can be added to a double bonded compound, and we get dichloride or dibromide. If we add bromine to a cyclic compound, it is very easy to see to predict that the addition of bromine can take place from top and bottom. But what we see is that the addition of two bromine atoms are in antiposition, and the corresponding other enantiomer is also formed. So in these reactions we get vicinal dihalide as reaction product. We want to use a non-nucleophilic solvent due to the intermediate that is formed, which we will see in the next slide. And it is important to run the reaction in the dark to avoid formation of active radicals. So the mechanism of this reaction is interesting. When you add bromine to a double bond, the first thing that happens is breaking of this pi bond and formation of two sigma bonds with bromine, making a positive charge at the center, and this is called the bromonium ion. And then this Br minus can attack the either carbon from two sides to give this product plus the corresponding enantiomer. And this addition makes it anti-addition. So if bromine comes from the bottom, this bromine goes up. So you get two bromine atoms bonded across the CC single bond. They are in antiposition. So in case of dihalide addition, it can open symmetric bromonium ions at either side. Always anti or trans addition of halogen takes place. Reaction products are enantiomers, but there is no specificity for this reaction. So it is always you get a racemic mixture in case of symmetric bromonium ions. You will get excess of one enantiomeric product in asymmetric cases. And this is a stereospecific reaction where one stereoisomeric form of the starting material reacts in such a way to form a specific stereoisomeric form of the product. So we will discuss about stereospecificity also in the next week. So from here we will continue in the next class.